Hi, in today's video, I'd like to do some sample calculations using Snell's Law. So first of all, a quick recap on what Snell's Law is. Snell's Law is a relationship, a mathematical expression that relates the two refractive indices and two angles, that being the angle of incidence and angle of refraction, for light interacting between boundaries of two medium. And it is as follows. Diagrammatically, it looks something like this. You've got your first material with a refractive index of N1, and you've got a second material. So this represents one material butted onto a second material, N1 and N2. Medium 1 and medium 2. Now, when we're making measurements of angles between two mediums, we don't measure against the surface, we measure against a normal. Okay, and a normal, as the name suggests, is a line that's at right angles to the interface between material 1 and material 2. So today, I want to have a look at 4 examples of applying Snell's Law. So our first example states that we need to calculate the angle of incidence for a wave light which travels from air into glass, forming an angle of refraction of 30 degrees. So let's set out our variables correctly. The angle of incidence is what we're trying to solve. That's the question mark for this example. We know there's an angle of refraction of 30 degrees. And we know the refractive index of air is 1. And we also know the refractive index of the glass, in this example, was stated to be 1.5. So, on our diagram, we have refractive index of the first material that's travelling from air into glass. Here's our diagram. So we know we have an angle of refraction, the light being refracted is 30 degrees. And we want to know what's the angle of incidence. What angle of incidence would cause an angle of refraction of 30 degrees? Here's our information set out. Here's our diagram. Let's now do the mathematics. So we're going to start with Snell's Law. Let's put some numbers in. N1 was just the number 1 times the sine of angle of incidence, we don't know. And N2 has a value of 1.5. Now, we know that the 1.5 is N2 and the 1 is N1 because the description of the question states that light is travelling from air, N1, the first medium, into glass, N2, the second medium. So that's why this is N1 and this is N2. And the angle of refraction was 30 degrees. Okay, now 1 times something just leaves us with angle of incidence. 1.5 times sine of 30. Now, sine of 30 actually gives us a half, but let's leave that as it is. 1.5 times sine of 30 degrees. I want the angle by itself. At the moment, we've got the sine of the angle of incidence. To get the angle of incidence by itself, I need to take the inverse sine. So the angle of incidence will be the inverse of 1.5 times sine of 30 degrees. Okay, now we get our calculator out, and we're using our calculator in degrees, not radians. That will give me an angle of incidence of 48.6 degrees. Example number 1. Example number 2 asks to calculate the refractive index of an unknown material X if light travelling from air at an angle of 45 enters into material X at an angle of 35. So once again, this is using Snell's Law. So, like we did previously, let's write down our variables. So the refractive index of X is our unknown. Our refractive index of air is always 1. We know that the angle of incidence is 45 degrees in this description, and we also know that the angle of refraction is 35 degrees. Okay, so let's try and draw this up. We know that there's an angle of incidence of 45 degrees. The description states that light is travelling from air, so the first refractive index must be a refractive index of 1.00. It's going into air. And it also states that it's travelling to an unknown refractive index, so we don't know it's travelling into, that's the second refractive index. That's what we're trying to calculate, N2. However, in this case, we are told that the angle of refraction is 35 degrees. So we do know that there's an angle of refraction of 35 degrees. Now you notice we can draw an arrow to indicate incident towards the interface and an arrow to describe the refracted away from the interface. There's our diagram. There's our variables. Let's use Snell's law again. Let's sub some values in. N1, our first refractive index, or our first material, was air. And the angle of incidence is 45. And that's going to be equal to N2, which is our unknown quantity, times our angle of refraction, which is the 35. Beautiful. Okay, so from here, we're after N2, that's what we're after. So N2 will be equal to the left-hand side, 1.00 times sine of 45, divided by this remaining, sine 35. Again, to get N2 by itself, at the moment on the right-hand side, it's multiplied by sine of 35. The reverse mathematical function to get rid of that is to divide by sine of 35. Do it to one side, we must do it to the other. So effectively, we're dividing this from the right to the left, and here's our new expression. When we substitute our numbers in using our calculator, making certain it's in degrees mode, we end up calculating the refractive index N2, and the unknown refractive index as 1.23. And again, this quantity is refractive index, so it is unitless. Question 2 done. Example number 3. Calculate the angle of refraction for a ray of light which travels from flint glass into air, given it has an angle of incidence of 25 degrees. So again, we have our equation. Let's write down our variables. In this case, we're asked to calculate the angle of refraction. We're told that the angle of incidence of the incoming beam was 25 degrees. We're also told that the refractive index of the flint glass in this question was 1.656. And as well as that, we're given the refractive index of air, and we know that to be 1.0. So let's have a look at this diagram. We have an incoming or an incident ray of light at an angle of 25 degrees. Now again, that angle is from the normal, not from the interface of the two materials. Now, in this description, the first material described says the ray of light is traveling from flint glass. So we're using this as our N1. The flint glass is going to be a value of 1.656. The question states the refracted light enters the medium, which is air. So in this case, the incident beam travels from material 1, which has a refractive index labelled N1, into material 2, which is air, that has a refractive index of 1.00. So here's all our variables. Here's all our diagram. Both complement each other. Let's write down Snell's law. Nice equation. Let's fill some values in. So first of all, N1 has a value of 1.656 times sine of the incident angle, which was 25 degrees. That's equal to N2, which is 1.00 times sine of the angle of refraction, which in this diagram we actually haven't even drawn. So let's draw this one in. Angle of refraction. Now, you notice this angle isn't bending towards the normal, this angle is bending away from the normal. And that occurs when the second refractive index is lower than the first refractive index. So, if N2 is less than N1, we find that there is a bend away from the normal. Okay, so that's how we can check these two numbers and predict the bend is going to be away. This angle of refraction should be greater than the angle of incidence. Let's do our calculations. Okay, in this case, we're after the angle of refraction. I'm after this quantity for now. So, one simplification, 1.656 times sine of 25 degrees. Now when I multiply that by 1, I'm just left with sine of QR. That's a lot easier, just gets rid of the 1. Okay, I want QR by itself. At the moment it has this mathematical function involving a sine. To get rid of the sine, I need to use the inverse sine function. Do it on one side, I must do it to the other. So my angle of refraction will be the inverse sine of 1.656 times the sine of 25 degrees. When we have to find an angle, we have to take the inverse of this more complicated looking mathematical expression. You've got to be careful with your calculator. Okay? Doing all that gives me an angle of refraction of 44.4 degrees. Again, you have to use your calculator in degrees modes for this mathematical step to be correct. Be careful with your use of parentheses or brackets to get this answer. So I have a refractive index of 1.656 for flint glass, an angle of incidence of 25 degrees, entering into medium 2, which is air, a refractive index of 1.0, we find the refracted beam will bend away from the normal because it has a lower refractive index than N1, and the angle it refracts away from the normal is found to be 44.4 degrees. Okay, the fourth and final example, let's have a look. Calculate the refractive index of an unknown material Y if a ray of light travelling from material Y has an incident angle of 30 degrees and refracts at an angle of 61 degrees in water. So let's first of all draw this one up. We've got an incoming ray at an incident angle of 30 degrees. Okay, now it refracts at an angle of 61 degrees. Again, it's bending away from the normal. That tells me that N2 must be less than N1. We know N1 is our unknown, our material Y, and we've been told that N2 was water with a refractive index of 1.333. Very precise. So let's write these down. The refractive index of material Y is question mark. The refractive index of the water was 1.333. The angle of incidence from our diagram is 30. And the angle of refraction from our diagram is 61 degrees. Okay, now let's write out Snell's Law. So N1 was our unknown quantity. N1. The angle of incidence is 30 degrees. N2 was our known second medium with a refractive index of 1.33. Sine, our angle of refraction is 61 degrees. Okay, we want N1 by itself. N1. At the moment, it's got times by sine 30. Now to move this over to the other side, so you leave N1 by itself, which is what we're trying to solve, instead of timesing by sine 30, I'm going to divide the right-hand side by sine 30. It's the reverse mathematics. So I've got a 1.333 times sine 61 degrees, all of which has been divided. Instead of multiplying by sine 30, I'm dividing both sides by sine 30, which cancels out here and leaves me with N1. But what I do on this side, I must do on the other side. So I'm dividing by sine 30. If I do my work for that, I find that N1, the unknown refractive index for material Y, has a value of 2.33. Example 4 completed. Summarising what we just did with those 4 examples, Let's look at transposing equations as a shortcut that some people might like to use on a cheat sheet. Let's say, first of all, that N1 is your unknown, in which case you can use the following equation. Let's say now that N2 is the unknown. Well, you can use the following transposed equation. Very good. Let's now consider what happens if we're looking for unknown angles. Say angle of incidence is the unknown we're searching for. In which case, or perhaps you've been asked to calculate the angle of refraction. In which case, so there's your 4 transposed equations, depending on which particular variable you're trying to calculate. It may be worth putting these on a summary sheet if they allow you to perform your calculations quicker with greater accuracy.
You've been watching a Juddy Productions video. If you've enjoyed and indeed learned something from this video, then please remember to like, share, comment, and subscribe. And as always, thanks for watching.